So in this example, we're going to look at, while it's not an example like we were having before, where we have an actual kind of maximum volume for an airline regulation or something like that, or a farmer's rectangle we can figure out. This is a little bit more in theory, but it's a very classic maximize or minimize problem. It says that we have a rectangle that we want to inscribe in a semicircle. This semicircle has a radius of 2. What we want to find out is what is the largest area of that rectangle that we can have inscribed in the semicircle, and what would its dimensions be? So reading through that, I know that I'm looking for the largest area of a rectangle. That right there tells me that I'm looking for the maximum, or I want to maximize the area of a rectangle. So area of a rectangle is usually given by the formula base times height. This would be our primary equation because it is the equation that we want to maximize. Now we know that we're going to have to come up with a secondary equation that somehow relates the base and the height, so I can substitute in. First, we need to probably draw a picture that represents what we're given here. We know that we have a semicircle of radius 2. So we're not told too much information here except that I have a semicircle of radius 2. So what I'm going to do is I am going to center my semicircle, and that's sort of a semicircle, on the where the center of my semicircle is at the origin. Because I know that from the center of my semicircle out to the edge is considered the radius, which is a distance of 2. So it helps if we'll center something like this at the origin. It makes things much easier. Now the next thing I know is I have a rectangle that's going to be inscribed inside of this semicircle. So in other words, it'll be drawn inside of the semicircle. So here's my rectangle. What we're trying to figure out are what would the dimensions of this rectangle need to be to maximize the area of this rectangle that is constrained, right? It has a constraint on it. It's constrained by the size of the semicircle it's inscribed in. So that's kind of the drawing for now. Let's put some labels on our drawing. And I know that for my rectangle, because ultimately I'm trying to find the area of this rectangle. So this rectangle, let's focus on just half of the rectangle for now. I know that this leg of this distance here would be a distance of x on this side of the rectangle. So from the center of the rectangle out to the edge of the rectangle is some distance x. I don't know what it is, but we'll call it x. Now the other problem here is I need to know what the height of this rectangle is. And the only thing I know for sure is that, again, the radius of this semicircle is 2. So I know from the center to the edge of the circle is 2, and I can draw that as I've done here, where this becomes almost a diagonal like that. So what do you see happening here? If I'm focusing in on just the rectangle here, or this image here in the first quadrant, I hope you see that I've drawn a triangle that has a base of x and a hypotenuse of 2. Now if I want to know what this other leg is over here of this right triangle that I just drew, then I would be able to use Pythagorean's theorem. And I know it's a right triangle, by the way, because this is a rectangle and all edges or all corners of a rectangle meet at a right angle. So let's think about that for just a second. If I have this triangle that has a hypotenuse of 2 and a base here of x, I've got to figure out what this extra leg is here. Remember that Pythagorean's theorem says that I've got one leg squared plus another leg squared, we'll call this h. And that's going to be equal to the hypotenuse squared, which is 2 squared. So if I wanted to solve this triangle for h, I would be able to say h squared is equal to 2 squared minus x squared, because I'm going to subtract x squared to the right. And then I can take the square root of both sides, and I find out that h would be equal to the square root of 2 squared, which is 4, minus x squared. And it's kind of up there at the top is our primary equation, but what we really ended up finding here, and I'm going to put this on my drawing so it's a little clearer, h is equal to the square root of 4 minus x squared. This formulation or this calculation that we did down here is what's giving me the secondary equation, if you'll notice that. So I'm taking what I know about a triangle and the constraints of that here, and I'm going to be able to substitute back into my information that we have over here as well. So now let's start to put some of this stuff back together. I know that my area, this is my primary equation, area is equal to, and it might be good for us to address the base. So the base of this rectangle is going to be x in the direction going to the right and x in the direction going to the left. So the base is, in actuality, let me put this here, base would be 2x's. So we have 2x times, height is now, we found this with our secondary equation, height can be written as the square root of 4 minus x squared. And what I now have is the area equation, or my primary equation, written in terms of a single variable that I can then take the derivative of. So let's simplify this before we do that. And I'm going to just take my area equation here, and I'll rewrite this as 2x times 4 minus x squared raised to the 1/2 power. So I took it out of its radical and wrote it as a rational. And now I'm going to take area and I'm going to take the derivative of that. So a prime. And when we're doing this, to be consistent, so let me move that out of the way, to be consistent with the way we've been working this, if I take the derivative, then 2x is going to be f, 2 would be f prime, g, because g would be 4 minus x squared raised to the 1/2, and therefore g prime is going to be the chain rule here, so I would have 1/2 4 minus x squared to the negative 1/2 times, that was the derivative of the outside. Now let's take the derivative of the inside, which would be negative 2x. And we'll simplify this. So I have, notice that this 2 is going to cancel with that 2. I end up with negative x times 4 minus x squared to the negative 1/2. And now I can put this together. So the derivative of a is going to be 2 times 4 minus x squared to the positive 1/2 plus 2x times negative x times 4 minus x squared to the negative 1/2. And it's just a challenge in simplifying from here. So we'll take this 2 times 4 minus x squared to the positive 1/2. I'm going to simplify the second term over here. I get minus 2x squared times 4 minus x squared to the negative 1/2. Notice that I have a 4 minus x squared in both of these terms. I also have a 2 in both of those terms. So let's take out a 2 and a 4 minus x squared. The smallest exponent I can take out is a negative 1/2. That leaves me with a 4 minus x squared in this term. Think about that before I go any further. Remember, if I take the what I just took out, multiply it back in, needs to give me back an exponent of 1/2. So when we multiply bases that are the same, we add the exponents, which is why this 4 minus x squared that's staying in the parentheses down here is to a power of 1, because negative 1/2 plus 1 is a positive 1/2. And let's see, minus an x squared. We can simplify further from here. I have 2 times 4 minus x squared to the negative 1/2 times 4 minus negative x squared, and a negative x squared would be 2x squared. And so I'm going to take the negative exponent here and I'm going to send it to the denominator. So I would have a 2 times 4 minus 2x squared in the numerator over 4 minus x squared to the 1/2 in the denominator. And I don't really need to go any further with that, because technically I'm going to set this equal to 0 and now solve. Ultimately, I want to find the critical values of this derivative. So when I set it equal to 0 and solve, I'm just going to take the numerator, 2 times 4 minus 2x squared equals to 0. Divide both sides by 2. I have 4 minus 2x squared equal to 0. Or 4 is equal to 2x squared. Divide both sides by 2. X squared would have to be equal to 2. Or x is equal to a plus or minus square root of 2. Now, before I go any further, we need to kind of consider a few things. First of all, we know that these values for x would be considered the critical values. I also know that the derivative is going to be undefined when x is equal to 2. So we would have also that, what were we calling this? A prime is undefined, does not exist at x equal to 2. But we need to kind of come back up here. So 2 and plus or minus the square root of 2 are the things that we're considering here. Remember that we're actually looking for a dimension, and so I can't have x equal to 2 because my value of x is going to actually have to be less than 2. The actual circle's radius is 2, and therefore the rectangle that's inscribed of it has to be some value just shy of the radius. Because if I had the rectangle in here and this length of x was equal to 2, I would no longer have a rectangle. So 2 isn't going to work, so I'm going to come down here and I'm going to get rid of the 2. It doesn't count. It's not a critical value that would be in my domain, technically, is what we're talking about, because the actual circle is 2. Now, what about the other two critical values, the plus or minus square root of 2? Remember, we're talking about a dimension here, and so I can't therefore have a dimension that is negative. So the only critical value that I'm looking at ends up being when x is equal to the square root of 2. The negative square root of 2 doesn't count. So if this is the critical value, let's make sure that it is in fact a max. We do that by testing around the square root of 2. So I'm just going to put the square root of 2 here, and we're going to evaluate the derivative to the left of the square root of 2 and to the right of the square root of 2. And when we do that, we find out to the left it's positive, to the right it's negative. And so we would be increasing to the left, decreasing to the right, and therefore, yes, this is a maximum value. So when x is equal to the square root of 2, coming back up here to our picture, when x is equal to the square root of 2, we have one portion of our picture that we're looking at. Now that question is asking me, what are the dimensions? What is the largest area and what are the dimensions? So I'm going to come down here and finish off what we were looking at. And so when we're down here, we know that we have our rectangle, which was the square root of 2 on the left of the center, the square root of 2 on the right of the center, and we had some height of that rectangle. Now remember, the height was equal to the square root of 4 minus our x value, 4 minus x squared, or in other words, the square root of 4 minus the square root of 2 squared. So 4 minus the square root of 2 squared is 2, so 4 minus 2, which is again the square root of 2. So we would have a height of the square root of 2. So the area that we found would be 2 times the square root of 2, representing the base, times the height of the square root of 2, or in other words, a maximum area of 2 times the square root of 2 times the square root of 2 is just 2, for a maximum area of 4. The dimensions, we said, is that the base of my rectangle is going to be 2 square roots of 2, and the height of my rectangle is the square root of 2. So all of that's to say the maximum area is 4, with a rectangular dimensions being the base 2 square roots of 2 and a height of square root of 2.